difficult. We're going to skip chain rule on second fundamental theorem of calculus. I was just going to justify why we get the answers we get, more, I don't know, better. But I'm not going to do that because I need all 20 minutes to do the trapezoid rule with you guys. Also, with LRAM, RRAM, and MRAM, we use the rectangles to approximate areas. What sort of geometric figure do you suppose we're going to use in using the trapezoid rule?
Triangles.
Exactly. Yeah, we're gonna use trapezoids, and that's yeah. The trapezoid rule means we're gonna approximate areas by using trapezoids. That means we're gonna do, and here let me write the name, trapezoid rule. Okay. If I've got some function like that, and I want to approximate the area from A to B, I'm not going to add up a bunch of rectangles, no siree, I'm going to add up a bunch of trapezoids. Here's what I'm going to do. Suppose I divided this region into a bunch of equally spaced partitions. Well, look who's here. Well, I'll get your stuff later on. So that means that I've got these y coordinates for these partitions. Okay, let's say that every partition is identical, every partition is delta x. Alrighty. Well, trapezoid rule, I don't have to decide who's going to be the height of my partition. Is it the y coordinate of the leftmost point? Is it the y coordinate of the rightmost point? Is it the y coordinate of the midpoint? No siree. I don't have to make those decisions at all. All I do is connect the dots. So I go, I just connect the dots. And do you see how by connecting the dots, how my little lines really hug the graph itself? I'm not like making these obvious cutoffs. Like, if you've got a graph and you've got to approximate it with rectangles, and you're going, well, look, my little rectangles are either way above or way below the graph. You see what I mean? Like with rectangles, because your top of the rectangle has to be horizontal, you always find yourself either underestimating or overestimating the areas. But with trapezoid rule, when you connect the dots like this, you're kind of hugging the graph. And so with trapezoid rule, ordinarily, you get a better approximation of the area than you would with one of the rectangular approximation methods. So, trapezoid rule, all things being equal, I use trapezoid rule when for my, area approximating needs. Let's go ahead and derive the formula for trapezoid rule. And once I derive the formula, you'll just mindlessly use the formula from here on in, okay? Let's say, okay, I've got to add up the areas of these trapezoids. Alrighty, I'm going to get the areas of these 1, 2, 3, 4, 5, 6 trapezoids. Alrighty, well, here, let me just make sure I'm doing this right. Let's say this height here is f of a, and this guy here is x1, so that height is going to be f of x1. And this guy is x2, so that height's going to be f of x2. And this guy is x3, and you don't have to write this down, you can just watch and enjoy. I'm not going to expect you to be able to recreate this derivation. Are you guys okay that I'm getting all of the heights of the endpoints of my partitions? And so this guy here is f of x5. Alrighty, this is x5. And then finally this guy is f of b. And now I'm just going to brute force. I'm just going to add up all 1, 2, 3, 4, 5, 6 of these trapezoids. Okay? And so like I said, I really don't need you to write this down. So here come the trapezoids. This first trapezoid, remember the area of a trapezoid is 1/2 times the sum of the bases. So this is, this is f of a. So I got f of a plus f of x1 times the height, which every height's identical. They're all delta x. Okay. And then I got the next trapezoid, this guy here. And its bases are x1 and x2. So I got 1/2 of f x1 plus f x2 times the height, which is delta x, plus 1/2 of f of x2 plus f of x3 times delta x. You see where this is headed? You know? And then I'm going to go da 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 until I get to the very last one, which is 1/2 times f of x5 plus f of b, okay, times delta x. Well, at this point, I can factor out the 1/2s, and I can factor out the delta x's. Because every term has a 1/2, and every term has a delta x. And now, let's see what I've got. I've got f of a plus f of x1 plus another f of x1. So that's 2f of x1, 2f of x sub 1. And then I've got an fx sub 2 and another f of x sub 2. So 2f of x sub 2s. How many f of x sub 3s do you suppose I have?
2.
Yeah. Why do you say 2?
Using it once for one trapezoid and another time for another trapezoid.
Thank you very much, Daniel. You guys okay with that? You're using f of x3 for the height, one of the bases of this trapezoid and one of the bases of that trapezoid. Good. So it would be 2f of x3 plus 2f of x4, because you're using f of x4 for 2 trapezoids, plus 2f of x5. But let me ask you this, how many f of b's are you going to have to use?
1.
Yeah, only 1. This guy is only used for this last trapezoid and none other. So you're going to use it right there. And ta-da, there's your formula for the trapezoid rule. Generally, the integral from a to b of f of x dx is going to be approximately equal to 1/2 times delta x times f of a plus 2f of x1 plus dot 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 plus 2f of xn minus 1 plus f of b. You know, essentially just remember that all the guys in between are doubled. The dudes on the ends are only represented once. And you multiply by 1/2 times delta x. And as before with the rectangular approximation, delta x is equal to b minus a over n, where n equals the number of trapezoids you want to use. So hey, let's do a couple and then we're done. Okay, or example number 1. Approximate the integral from 1 to 3 of x squared dx using trapezoid rule, n equals 4, using 4 trapezoids. What do you suppose I would recommend that you do first? Please graph it. Please graph it and then do that thing. See how clever you guys are. If you're stuck, then let's go ahead and find what delta x is. Are you guys okay that delta x is always b minus a over n? Usually you'll just be able to use your cleverness. I mean, if you're going to partition 1 to 3 with four partitions, then obviously the width of each partition is a half. So you get 4 partitions. But if you can't figure that out, you can always just go delta x equals b minus a over n. So the area is approximately 1/2 times delta x, which is 1/2. And then just use all your things. F of 1 plus 2f of 1.5 plus 2f of 2 plus 2f of 2.5 plus f of 3. Sorry about my coughing. Fourth, f of 1 is 1. 2.25, double that is 4.5. 4, double that is 8. 6.25 doubled is 12.5 plus 9. I don't know why I'm using my calculator. I could have done this all in my head. So, how many people here got 8.75? Angel, Kylie, good 2 of you. Well, you know, if 2 people learned and 32 don't learn, that's okay. I did my job. I succeeded. Is there a problem? Did I go too fast? Am I wrong? Is 8.75? Kimberly, did you get 8.75? How many people, when I asked who got 8.75, didn't raise their hand because it's early in the morning, they're too lazy to raise their hands? Cool. But you know, I just got you to raise your hands. So I guess it was a different context. Okay. But I appreciate it. Any questions? So very few of you got this. Is there some problem here? Am I going too fast? Is this not making sense? Abigail, is this okay?
I mean, I was just working on it.
Oh, okay. Yeah, maybe you guys, see the problem is you don't rely on your ability to do things in your head enough. You know? Just do it in your head. My head's way quicker than a calculator. Every person in this class is smarter than their calculator. Okay, well, hey, let's do another one. Oh, by the way, what's the real answer? Well, it's going to be the integral from 1 to 3 of x squared dx, which is 1/3 x to the third evaluated from 1 to 3. So it's 27 over 3 minus 1 over 3, which is 26 over 3, which is 8 2/3. So I think that's pretty close. 8.67 versus 8 2/3. Why are people being so loud out there? Mr. They must be Mr. Lauder students. Okay. Next. Are you guys ready to do another one? Okay, maybe you guys will get this one done fast. And then I've got to do one involving data table. Okay. Here we go. Example number 2. The integral from 1 to 2 of radical, oh wait, there's a sub. N equals 4. Oh, you saw him?
And they're doing that.
Oh, okay, my bad then. I know he has to go to one of those NGSS meetings, but I thought it was today, but maybe it was tomorrow. Okay, well anyway, hey guys, please do this. Do this now.
Trapezoid.
Yeah, trapezoid rule. And you'll have to use your calculator. You can't do this in your head, because I don't know what the square root of 1 1/4 is offhand. And then I've got to zippity doo-dah you through a data one. that. I'm going to have to do keep working with, do you notice I always like to do this first step where I do F of. I don't try to just haul off and start doing the punchy. I like to at least write this down so it greatly reduces my chances of making a mistake. So I urge you guys to write that first step down. It only takes a few seconds, but it really ensures that you don't make a mistake, you know, or you end up forgetting terms. At this point, you can do it however you like. Remember, the first and last terms only count once. Is anyone getting approximately 1.218? Okay, good for you guys. Any question or problem on this? Okay. Just 1 second. Clear. They cleared there. What is it, 1 to 2? I could do it the long way, but okay, here's the thing. Actually, alrighty, the integral from 1 to 2 of radical x dx is approximately equal to 1.219. So here's the one thing I want you to notice. This graph, my trapezoids ended up underestimating the area. The true area was bigger. True area is bigger, okay, than what the trapezoid rule approximates. But look at this guy. Did you notice how here the true area was smaller? Why would that be? Why would trapezoids overestimate the area in this graph, but underestimate the area of that graph? What was it about those graphs that made it that way? Yes, Leilani?
The concavity.
Thank you. You guys okay with that? That's something they want you to know. You can't say because it was increasing. Remember with rectangles, if you're increasing, then LRAM underestimates and RM overestimates and all that stuff if it's increasing or decreasing. But here, these are both increasing. But one guy the approximation is too big, and here the approximation is too small, and it's just what Leilani said. And I want you to have that in your head. You can always just make a drawing and estimate it. And the thing is, because the graph is concave down, if the graph is concave down, alrighty, then the true area is going to be bigger than your approximation. But if the graph is concave up, the true area is going to be smaller than your approximation. Graph concave up. approximation. Okay, the approximation overshoots. Okay, hey guys, that's tonight's homework. Can just give me a moment. I didn't get a chance to talk about data tables, so I may have to remove a problem from your homework. 7. You know what? I think I'm going to remove